Okay, so I would like to thank the registered people and New Star Systems also for asking to develop and promote this webinar. We will be discussing about magnetic shielding for future space missions. The panel will be made by our three panelists, which will have Dr. Andrea Lani, who's a research expert at the Center for Mathematical Plasma Astrophysics. He's also the director of the Leuven Computational Model Center at KUL, and also a guest research expert at VKI. Andrea has 18 years of activity focused on space re-entry, aerothermodynamics, plasma modeling, numerical algorithm, and scientific HPC and software engineering. Welcome, Andrea. Then we have Manuel Rosa Betancourt, the CEO of Neutronstar Systems, who from 2019, Manuel dedicated full-time to setting up his Neutronstar Systems company. And then we have also Marcus Collier-Wright, the CTO of Neutronstar Systems. He moved in Germany in 2018 to work on an electric propulsion system at Ariane Group before committing full-time to Neutronstar Systems from July 2019. Thank you to the panelists. We'll now move on to my other slides. So welcome to the webinar from the Access Space Alliance. We've been promoting the new space sector for nearly a couple of years now, since our inception in 2019. We've been having webinars since last year, 1 year, April 2020, when the lockdown for the COVID pandemic started here in the UK. And today's agenda is as follows. So this introduction slides for myself. Then we'll go straight to the presentation of the projects that we will be discussing through the panel, and then a short panel discussion as well after that, and a Q&A where all the attendees to this webinar will be able to ask questions. If you would like to ask questions, at the bottom of your screen, there is a Q&A box where you can actually lodge your questions in there. Thank you so much. Just to say that the proprietary and copyrights of this webinar will be retained by the Access Space Alliance, and that if you would like to have more information on the Access Space Alliance, please look at our website for joining the Access Space Alliance. On the Access Space Alliance, we have three directors, myself, Betty, and Christians. We are based in different countries in the UK and in Germany. The Access Space Alliance, many of you already know about it, is the uniting and representing the new space sector into connecting, advising, advocating policies and views, as well as promoting research, education, and standardizing also particular technologies as well. We have started a new life at the Access Space Alliance from the beginning of 2021. We have formalized the alliance, so we are now a formal organization with membership and terms and conditions and for membership and fees. We are organizing our first board council in April, and so will be a council of members to the Alliance. This year's activities will range between these webinars like this, roundtables and talks and lectures, as well as committees. I'll tell you on the next slides what they're about. We're organizing also a conference at the beginning of May. Of those that are interested to attend as speakers, panelists, keynote speakers as well, just email me and I will provide you more information. We will be organizing other activities as well throughout the year. Any webinar from the past, and also including this one, will be placed on the YouTube channel. You can search on YouTube Access Space Alliance, and you will actually look at all the recording freely available for you to watch. On the committees I just mentioned earlier, we have now 4 committees. One on free space optical communications, one on regulatory and space policy, one on lunar deployment committee, of which we're having a series of webinars also on lunar deployment, and recently we formed the finance committee for the members. More information, please write to myself. Today's webinar, we have nearly 98 registered individuals from 36 different countries. Many, of course, are from Europe. In terms of companies versus the size of the company, you'll see there are nearly about 43 to 44 companies around the world with 1 to 20 employees. Of course, we have also companies registered up to more than 10,000 employees as well. So you see the distribution of these companies in this chart. We are now ready to start the webinar, and I will like to get the panelists now to make the presentation.
Thanks a lot for the introduction, Tony. So I'm going to take over the screen sharing, and I'm going to go full screen. Can you just let me know that you guys can see this okay?
Yep, it's fine. Thank you.
All right, guys. Well, firstly, thank you to everyone for attending the webinar. I'll be introducing to you MEESST, Magnetic Shielding for Future Space Missions. Just a quick intro of our panel. Tony already gave us a very nice introduction, and I also wanted to just inform you guys about the specific roles we have on the project. So Andrea is the project coordinator, managing the whole project execution. Manuel and myself are working on the project dissemination. So just to give you an overview of what we're going to cover in the webinar today, I'll give a brief introduction to the research that we're doing in its context, the solution that we're trying to provide, the main differentiators in our approach, and then I'll go into some detail on the project consortium and look also at the various applications of this technology before wrapping up and opening the floor to a panel discussion and some questions. And at the end of the webinar, we got a, let's say, a premiere event for you guys if you stay till the end. So look forward to that one. So what is the context that we're addressing here? We're addressing the problem of spacecraft re-entry, and this is one of the most challenging parts of any space missions. Spacecraft obviously travel at very high speeds when they're in space, and when they return to a planet, they come into contact at these high speeds with atmospheric gases. And what this results in is a compression of these gases, a huge amount of friction generated, and this leads to generation of heat and the formation of a plasma around the spacecraft. This leads to two main issues. Firstly, the heat that is generated causes intense temperatures on the surface of the spacecraft, which can really damage the structure of the spacecraft and potentially lead to failures. And the second problem is something called the radio communications blackout. This happens because the plasma from the gases envelops the spacecraft and actually prevents any radio signals traveling through it, meaning that the spacecraft can't communicate with the ground station, with mission controllers, and it can't transmit any data during its descent. And this is really quite a significant issue. At the moment, this problem is attempted to be solved using physical thermal protection systems. And we have here an image of a human landing capsule from the United States. And what you see is that it's covered in these tiles, which, as you can see, are marked by the heat of the re-entry. But these tiles are very heavy, and they're only quite limited in the protection that they provide. This is another example of the types of tiles that are used, and this is quite a famous example. It's the Space Shuttle. Of course, the Space Shuttle was one of the most used designs for flying into space and returning from space, and they also use these physical protection systems, but they come with several drawbacks. Firstly, they're very expensive to design and implement. They're heavy. They take up a lot of mass of the spacecraft. In terms of designing them, this takes a long time. It has to be optimized to specific mission needs. They're not reusable. A lot of these tiles had to be replaced after every single flight. And also, they don't address the issue of radio blackout. So even though they protect the spacecraft somewhat from the high heat loads, they still remain the problem that mission control could not communicate with the spacecraft during the re-entry. Perhaps most importantly, there's a significant failure risk associated with this method, and this was obviously demonstrated with the terrible events that happened on the Space Shuttle Columbia, where one of the tiles failed, and this led to the loss of the spacecraft and the loss of the crew. So what is the solution that we are trying to bring with the MEESST project? We are here to apply the phenomenon of MHD, or Magnetohydrodynamics, to this problem. Magnetohydrodynamics is referring to an interaction between electromagnetic fields and an electrically conductive fluid, such as a plasma. And the idea is that we can apply it to space transportation vehicles by generating a magnetic field, which interacts with the plasma that forms in front of the spacecraft and deflects these charged particles and shields the spacecraft from the heat that is generated. With this principle, we should be able to reduce the heat fluxes and eliminate the telecommunications blackout. And for this, we have a couple of requirements. We need a very strong magnetic field in order to make the solution effective, but also because it's a spacecraft and we're trying to reduce mass and make it as cost effective as possible, The system needs to be very lightweight and it needs to be very compact. This phenomenon has already been investigated here on Earth in some laboratories, and this was done in the University of Stuttgart. You have here is a picture of one of their plasma wind tunnels. These are really amazing facilities where they generate a very hot ionized gas and they blast it at high speed into a test chamber. And you can really try and investigate what happens to probes and test samples in these gases. And what you see on the right here is an observation from one of these experiments. And well, we have an example here of a probe in this plasma flow, where it's either operating with a magnetic field, as in the bottom half, or without a magnetic field. And this is what we do at the moment in space. We have no magnetic field, and what you can see is that the very hot gas is right next to the surface of the probe, and this is causing then a lot of heat and a lot of risk onto the probe or the spacecraft. When you have a magnetic field applied, you can see that the effect is that the high temperature and the very intense part of the plasma is offset away from the tip of the probe, and this is exactly the principle that we are trying to build on. Now, this was made with quite a weak magnetic field using permanent magnets, and this is where we bring our differentiator with this project, which is the use of high temperature superconductors. A superconductor is a material which can conduct a lot of electricity without any electrical resistance. What this means is that we can conduct the same amount of electricity as a conventional cable, but with much, much smaller cables with much lower mass and in a much more compact area. And here is a comparison point between a superconducting cable, which carries the same amount of current as this huge stack of cables made from conventional technologies. It's quite clear that they have huge offerings in savings on mass and volume. Not only this, but they're now very much commercially available. Here's some pictures from one of our consortium partners, Teva, who are producers of superconductors, and they're now available off the shelf at very reasonable costs with a very scalable manufacturing process, and they're very much commercial products. They've been used in terrestrial applications for medicine, for healthcare, for wind energy generation, for power transmission, you name it. There's so many applications, and now we're trying to bring them into the space domain. So with these high temperature superconductors, we will be building a magnet which provides a magnetic field, a stronger magnetic field than has been done in the past, and which will help to reduce the radio communication blackout in a much more lightweight and effective way. MEESST will fundamentally enable several benefits. Firstly, accurate positioning for reusable space transportation vehicles. It will allow us to increase the amount of data that can be transmitted by scientific capsules during re-entry. And it will also fundamentally allow a much more light and compact thermal protection system for vehicles for several mission applications, which I'll go into in a little bit more detail later. But for example, for spacecraft returning from the moon, from Mars, and from asteroids. Perhaps most importantly, with this project, we will contribute to a shift in focus in design for spacecraft shielding, away from material design to magnetic shielding, and fundamentally, we will maximize the cost effectiveness of space missions. So we have a really fantastic technology here, which we are looking forward to researching and developing, and we have a great consortium to do so. We have in total 10 consortium partners, consisting of 6 universities and research institutes, and 4 SMEs. So we have a fantastic mix of academia and industry. We're also well represented across Europe, with 2 of the institutes coming from Belgium, 4 from Germany, and representation also from France, from the United Kingdom, from Switzerland, and from Luxembourg. And I'm going to go down into a little bit more detail on some of the partners and structuring them into the 3 main areas of responsibility that they have in the project. Starting first with the project coordinator and one of the lead simulation partners, which is the Catholic University of Leuven. So Leuven will be coordinating the project, but also contributing with some numerical simulation codes for plasma and re-entry simulation. And here they're building on a very significant expertise on space weather events, on Magnetohydrodynamics, and on mathematical astrophysics. In addition, supporting on the simulation work, we have the University of Southampton from the United Kingdom, who are actually leading the work of harmonizing all the various numerical tools and verifying them against experimental data. And they also build on a really excellent astronautics heritage and one of the most leading aerospace engineering departments anywhere in Europe. We have the University of Luxembourg, who are playing a very unique and actually especially important role in this project. because they're working on ray tracing algorithms for the radio blackout. And this is really interesting because this allows you to predict exactly where the radio waves can pass through the plasma layer behind the spacecraft. And by making use of the tools that they offer, we can really maximize the effectiveness of being able to communicate even during re-entry. Finally, on the simulation side, we have AEDS. This is a small consultancy based in Switzerland, and they'll be supporting us with the numerical studies of the radiation effects and also some of the plasma simulation verifications. Moving on now to the simulation capabilities of these partners. We have a lot of codes here from different universities who have developed their own codes, and part of the challenge in this project is to really harmonize and bring together all of these codes and make sure that they're all validated against each other. So we have Cool Fluid, which is a code from Leuven, and also the Von Karman Institute in Belgium, which is really quite well suited for combining fluid dynamics and magnetohydrodynamics. We have OPTA, which is from the University of Southampton, which is more focused on the plasma physics simulations. We also have SAMSA, which is a code from the University of Stuttgart, which is really quite good at describing the magnetohydrodynamic effects. And finally, the code Borat from Luxembourg, which is used for ray tracing. So one of the main challenges and achievements that we hope to bring with this project is the harmonization and combination of these codes into a very well harmonized tool that we can use for further design and verification activities. So moving on now to the actual partners who will be developing the magnet and the prototype that we're going to be testing in this project. The leader for this part of the project is Absolute System. They're a cryogenic specialist from the south of France. So they'll be working on the system engineering of the magnet and also providing the cryogenic system which is needed to keep the superconductors cool. Speaking of the superconductors, we have Teva as part of the consortium. This is the largest producer in Europe of commercial superconducting tape. They have capacity of over 1,000 kilometers per year, and they'll be providing the raw tape, which is used for the magnet, as well as supporting its design and production. And finally, we count as well on the Karlsruhe Institute of Technology from Germany. They're one of the foremost leading universities in Germany in the field of superconductivity. And they'll be responsible for manufacturing the magnet and performing the design through multi-physics simulations. And on this slide, I just wanted to point out these pictures on the right, which is a representative experiment that was already run in collaboration with the DLR, showing the effect of a magnetic field, again, on the reduction of the heat flux of a probe in a plasma wind tunnel. Finally, I'll come to the testing partners. And the testing here is really important because it's going to allow us to test that the prototype magnet works, and it's going to allow us to verify and validate the numerical codes against the results we get from the testing, because the simulation codes are only as good as what they can prove. So we start with IRS, it's the Institute of Spaceflight Systems from the University of Stuttgart, and they're going to be leading the experimental studies for the heat flux mitigation in terms of putting the magnet in a wind tunnel and seeing that we can reduce the heat flux. They're also supporting the design of the magnet, and as mentioned before, they're providing some numerical tools which will be part of the harmonization process. We also have the Von Karman Institute of Fluid Dynamics from Belgium. They also have experimental facilities for testing probes in plasma wind tunnels, and from their side, they're going to be contributing mainly on the experimental tests for the blackout mitigation, so understanding exactly what effect the magnet has on the effect of the radio communications through the antenna. I wanted to also give a brief overview of the facilities that we have available to us in this project. Again, from VKI and from IRS. We have excellent world-class facilities from both partners. VKI have a plasmatron, which is used, as I mentioned, for these radio communication blackout effects. And in here, we'll be testing both the probe without a magnet and with the magnet to understand exactly how much we can improve the radio blackout mitigation issue. The University of Stuttgart has very widespread facilities which are used not just for aerothermodynamics, but also for electric propulsion. And here we will be testing the impact that the magnet has on the mitigation of the thermal loads and the heat fluxes. Finally, Neutronstar Systems, we're the 10th partner in the consortium. And our role is focused on the dissemination, both within and outside the consortium, on publication and publicizing the project, and also on exploiting the results of the project in a commercial sense. As a company, we're a startup who are focused on the development of superconductor-based spacecraft systems. So we see MEESST certainly as a very much candidate technology for future commercialization in this sense. In addition to this, we're also working on electric propulsion systems using superconductors. And this is a prototype in the bottom corner you see here, which we are working together with the University of Stuttgart. So that's the consortium. As you can see, we have quite a wide range of different expertise and different backgrounds. But what I wanted to get into a little bit now is the kind of applications that you can use this technology. And really, they're almost limitless. But I'm going to focus on the ones which are in the near term and the midterm. So already we could potentially utilize this technology for shielding spacecraft which are returning astronauts from the space station, for example. As mentioned with the space shuttle and some of the other spacecraft that I showed earlier, at the moment they're using these very heavy thermal protection systems, and with the use of MEESST, we really are going to be trying to reduce that mass, increase the available payload, and make it much more cost effective. We can also use this for sample return missions. So for example, the ESA Mars sample return mission, which will be launching in 2026. This is going to travel all the way to Mars, capture some Mars samples, which are being collected by the Perseverance rover, which of course landed just last month, and bring them all the way back to Earth. And this is really a very ambitious and fascinating project. But the final challenge of that whole mission will be for the samples to survive the journey back through Earth's atmosphere. And this is exactly the kind of application where you can make use of MEESST technology. Looking a little bit further ahead now, we also see that we can use this for lunar missions. Again, if you're looking at transferring lunar cargo from the moon back to the Earth, or humans coming back from lunar, like with the Artemis program in the USA. We can use this for asteroid mining. If you're going to be mining valuable resources from asteroids and bring them back to Earth, they're going to need a re-entry shielding system. But you don't need to use this just on Earth, you can use it on Mars as well. And here we have further applications using it for Mars cargo, if we want to deliver large quantities of cargo to Mars to support any human presence on the Mars. And finally, for interplanetary crewed flight missions, where again, any crew and any humans on board the spacecraft will need to be shielded as they travel through Mars' atmosphere. So to summarize everything which I said today, with MEESST, we are addressing the issue that atmospheric re-entry poses for spacecraft, which is the fact that communications become disruptive and there's large heat fluxes are generated, which can damage and risk the safety of the spacecraft. By using Magnetohydrodynamic principles, we will try and bring a solution for this problem. We'll be using high temperature superconducting coils in order to generate a large magnetic field, which shields the spacecraft as it comes through an atmosphere. And with this, we can offer a more lightweight and more cost-effective solution than the status quo. In order to do this project, we've built a multidisciplinary and pan-European consortium. We have companies from 6 different countries around Europe. We have a really excellent mix of academia and industry, and every company on this list is a leader in their respective field. And really with MEESST, what we're going to be able to do is increase the technology readiness level of this technology from its current level of about 1 or 2 up to TRL4, and shift the focus away from material design to magnetic design for shielding spacecraft, and therefore bring in a new design paradigm for future space missions. So thank you very much for listening to the presentation. We'll be happy to take any questions, and we also invite you to get in touch if you'd like to learn more about the project.
Great, thank you, Marcus. Is there any words from Andrea and Manuel on this as well?
Absolutely, I just give the chance, Andrea, please.
Well, this project is a sort of dream for any aerospace engineer. And I must admit that it was so exciting to be involved in that, and then having the chance also to take the lead and then bring it to success at the first attempt was also like quite a challenge. Yeah, we managed to build a very strong consortium with very diversified expertise. And the project is, I think one of the key of the project, first of all, is that it, let's say it inspire people in some way, because we are used to watch all these sci-fi movies in which all these fancy spacecrafts can use magnetic field to do something, let's say, to improve their performance, but we are actually not able really to fly this kind of technology. And also, when you deal with something with such a complicated problem, you always need a multidisciplinary approach. And so here we clearly have an integrated approach where we combine numerical modeling, experiments in different facilities, and also manufacturing. So, I mean, it's just a milestone for this kind of technology, but it can be really a major one to somehow allow a paradigm shift a bit in space technology, because now most of the focus for re-entry is into designing thermal protection systems, so material science. But with this project, we hope to shift a bit let's say, the focus on magnets, superconductors, and you know, so potentially we can play a big role, let's say, in this, and hopefully we'll be very successful.
Okay. Thank you, Andrea. I mean, from my side, Tony, thank you, Marcus, for the presentation. You need to brief a little bit, my friend, you see, because you. But it was really, really thrilling. I love the topic too, and well, I'm coming from the material science part, and I just found it fascinating. I found it fascinating because. From the material engineering side, I could understand too much about the codes at the beginning. But what I could understand is by the combination of numerical codes and a good piece of engineering containing superconductors, we can really demonstrate the principles of this application. And that is something that, as Andrea said before, is groundbreaking. And it also opens new possibilities, because it shifts the paradigm to a situation in which spacecraft needs to be designed for re-entry, just, you know, based on the freedom of design that superconductors can provide to you, and shield spacecraft in a way that you bring the payload safer and cheap and faster to its destination. So I think this will become a major issue in the future, especially, you know, when we're talking about a moon economy, etc. We will need to think about disruptive solutions for these problems, and this is exactly this. And I think that from the principle of the funding, I think that the EU is doing its bit on funding this kind of disruptive technology, since it also light the spark of inspiration for, yeah, as you say, Andrea, space engineering, material engineers, also people doing codes and simulating. So I think it's really a great project. I'm really happy to be here and tell you about it. Thank you.
Okay, thank you so much for the presentation and the additional remarks made by Andrea and Manuel. Now I would like to open the discussion and questions for discussion panel. I have a set of questions for you. So we will start with that. We'll have about 15-20 minutes of this discussion, and then after that we will ask the attendees to ask their questions, and I can help with that as well. The first question, well, let me say that I'm really happy to see that we are a step closer to the Star Trek Enterprise, where we have these sort of shields that protect the Enterprise from many threats, basically. So a step closer to science fiction. Excellent. So the first question I have for you guys, Andrea, Marcus, and Manuel, what are the main challenges of harmonizing the numerical codes, and why this is important?
So, Andrea, this is you.
I'll take this one. Well, as you see, we have different partners, each one coming with their own numerical codes and also different models. The models between one or the other partner differ significantly in some cases. And the thing is, for instance, we have single multi-fluid models. The chemical model can be different. The schemes that we use can be different. And also the treatment of electromagnetic field can be significantly different. But what we try to do is to build, to let's say, create some tool which will give us confidence, despite all the differences, to reproduce, to rebuild the experimental results. And a way that we are trying to mitigate these differences is to try to share some tools within the consortium and to couple them with our flow solvers, our plasma solvers. For instance, we have established a collaboration with the University of Illinois, which is developing a library called Plato, which basically provides all the thermochemical and radiative properties for plasmas. And this is already integrated in Cool Fluid, which is the software that we use at KU Leuven and VKI. Is not integrated into the software from University of Southampton. But of course, once they are able to get the thermodynamics, the chemistry, and the radiation from the same library, we will already minimize some of these differences. And then when we compare the numerical solutions, I mean, if we see a difference, we can explain it. I mean, let's say the possible explanation for the difference are more confined. And also another step towards this harmonization is to try to share this ray tracing algorithm to basically track the signal, study the propagation of signals through the plasma sheet around the vehicle. And in this case, all the codes basically will be coupled to this Borat software that does the ray tracing, which is developed by the University of Luxembourg. So there is basically two steps in the project. The first one is a verification. So we have already some experiments and some numerical simulation from IRS of an experiment of heat flux measurement on a probe in supersonic conditions. And we also have numerical simulation for that. And so what we want to do is to rebuild this result and compare with the reference results we have. Once we are able to, let's say, among all the partners, reproduce the same results or very similar, or explain the difference between the different code, then we can move forward and go to the validation phase, where we will have a new set of experiments, this time not in argon, but in air and CO2 mixtures to reproduce, you know, the entry in Earth and Mars atmospheres. And yeah, and that basically will be a major part of the project, to be able to do experiments and also to validate it with different tools.
Okay. Unless there's any other reply on this, I'll go to the next questions. We have about 20 minutes left. Beyond the reduction of the mass and volume, what other benefits does the use of superconductor offer?
Well, I mean, yeah, I'm gonna take this one because Marcos is looking at me already like this is for you. No, you have also the advantage that superconductors can bring to develop other spacecraft subsystems. So, for example, propulsion systems can be based on superconductors. You can also assure that you can get enough current to generate magnetic fields high enough for bigger spacecraft. So for that, you will need the additional added value that superconductor brings, which is as they allow you to upscale your power without severe mass penalties and also efficiency penalties. Since with the use of high temperature superconductors, you will have zero losses. So this is something that you can be also used on, for example, power appliances for power management and distribution, especially in large missions. You will have substantial amounts of power needed for propulsion, especially in the case of crew missions or cargo missions. And the transmission of this power will require compact and lightweight, efficient subsystems. And another one, last but not least, it could be also called the cosmic radiation systems, or cosmic radiation protection systems, sorry. These ones could be used to protect astronauts and yeah, space travelers, for example, if going to Mars. So I think that the superconductor allows you also, in the way of the magnet design, you have a very high degree of freedom for your spacecraft, because all what you need to do is design your spacecraft in a way that aerothermodynamically and based on the existing tools is big enough and large enough to sustain the magnet systems around its core and protect the spacecraft, and B, also allowing the necessary power that is needed to operate this magnet. And I think that you wouldn't be able to build this technology if you wouldn't have superconductors. And that's the enabling power of that the technology brings.
So Manuel, on the next question, it's very simple. What can you use these superconductors for in space applications? What are the other applications that you can actually use them for?
Yeah, I think you mentioned most of them. But exactly, like, I mean, to summarize, the propulsion, the power management, this is important because you remember the picture of the cables I showed, these huge heavy cables, especially to higher powers, you could completely reduce it down. One other niche application that we found recently, and we're now working together with ESA on a contract, is for using these superconductors for scientific instrumentation, because these instruments need to be operating at extremely low temperatures, minus 270 degrees. And they can only do that if you have a cable which doesn't generate any heat, and there has to be a superconductor. So it's not something we thought of immediately, I have to say, but ESA have also seen the benefit of using this for space, and we have to applaud that.
Okay, thank you. Maybe the last questions, then we'll move to Q&As. Which near-term missions could the MEESST systems be used on?
Yeah, so I think I also mentioned this a little bit on the presentation. Really, any mission where you're going to be re-entering, especially those where you're coming from further away than low Earth orbit. The Mars sample return, I think, is the best example. And there you have multiple parts of that mission where you could use it, because you have a capsule which needs to enter Mars and go down to the surface of Mars to collect the samples. So here it needs shielding. But then when it comes back to to Earth, you again need to shield it when it comes back in for the re-entry on the Earth side. So there's even two stages of that. Also, we're considering, as a way to get an accelerated in-orbit demonstration of the technology, is to really miniaturize the superconducting coil and see if we can put it on a CubeSat and even test it out in orbit, deorbit the CubeSat and see if we can generate some useful data. So Mars sample return is in 2026, but you might even see this flying in space in the next 2 years if all goes well.
Okay, so it's actually a great technology to reuse it over and over again. It's not like the existing technology, which is only a one-time use, basically. So,
yeah, you have, yeah, for very good. I mean, exactly, I think right, that yeah. Greta would agree with this technology if she had the chance. So, yeah.
Miniaturization, I suppose, and also reduction in costs for space missions. That's what I can see, in effect. Last questions, just to have a little bit more of a view of your next steps on the project, and when could such systems be used in space?
Well, so this project started in October. It will run for 3 more years. And at the end of these 3 more years, according to what we subscribe for, we should have a prototype that has been tested within our plasma facilities. Definitely not something that you can already take and put on a spacecraft. So you need at least another project to get to that point. Now, actually, we were discussing recently with Manuel the next necessary step is to find the cheapest possible way to fly this technology, and also in the shortest time. So probably, as Marcus mentioned, the CubeSat idea is what we will try to go for. So CubeSats are becoming a very successful business and way to launch any kind of experiment in space, and also, yeah, with very limited cost. So that will be something that we will propose to the European Commission and try to get this demonstrated in a real flight.
Okay.
I mean, it's actually, yeah, I completely agree with you. And it's actually, it's an interesting, can be something done off the shelf, you see, Tony. So it's the important thing is the collection of the experimental data to demonstrate and keep building on the work that is being done.
I think it's a great idea and technology. So I look forward to seeing it soon. I'm going to open up now the Q&A for the attendees. We now have about 10 different questions. May I suggest that I ask the question, someone answers it, and then afterwards, if you can actually write the questions physically on the screen to be saved if you want. You don't have to do that, but let me just start off with the first question. So anonymous attendee said, what is the power per shield surface required by this magnetic shield?
There's not necessarily a specific link between the power you need and the amount of surface you have, and that's the beauty of the superconductors. In theory, you can just make larger coils and put more electricity on them, but once the electricity is in the coil and the field is generated, you don't need to be providing more power. Because superconductors don't lose their power. That's the fundamental characteristic which makes them so brilliant. So it's a very scalable solution. We can use it on existing size spacecraft, and it should be pretty feasible to scale it up to larger ones as well.
Okay, next question. Pierpaolo Gigino, you don't have a question on the screen. If you want to retype it, I will come back to you later. Claudio Voto's questions, any interference with human bodies in the spacecraft?
We're not expecting anything. At the end of the day, this is very similar to when you go for an MRI scan. You lie down in the machine and it makes the magnetic field around you. You just have to make sure you're not wearing any watches or belts, and then you should survive.
Yeah, well, I mean, I'm not sure about the configuration of the magnet and the impact to the human body. But what I think is something that is a great question, actually. And I mean, in terms of the general interaction of the human body with magnetic fields, I don't think it's going to be a real problem. The main problem will be to have a spacecraft that generates a magnet design where the human body is not going to be affected, you see. And for this, we need to do electromagnetic compatibility, and it has to be looked at a lot of stuff. But at first, I think that the important key of this technology is to use this to accelerate colonization of, for example, Mars, or to accelerate commercialization of operations in the moon, to bring material from the moon to Earth, to bring astronauts potentially. So I think that yeah, it will be interesting to look at this topic. Yeah, in the future?
Yeah, I suspect that the electromagnetic field is closely around the surface of the spacecraft. Is very strong, very close to the surface actually to deflect the plasma, the outside plasma, and that maybe there's enough distance between the shield and the human inside, I suspect, to reduce the amount of let's say electromagnetic radiation, call it a magnetic field into the body of a human inside, I suspect. Okay, I think I'm going to move to the next question, which is basically from David D. What are the limiting factors stopping you from using an even stronger magnetic field?
I mean, in principle, not too many. There are some sort of specific things we have to think about. From the side of the superconductor, the stronger the magnetic field, the lower you have to cool it. But this is only for really, really strong magnetic fields. At the end of the day, we're going to generate a field which is effective enough at shielding the spacecraft, because we expect there'll be some saturation point at which the effectiveness of increasing the magnetic field is not so effective anymore. And as discussed in the last question as well, the electromagnetic compatibility, this will be the trade-off that we have to make. But with the design flexibility we have quite a large range of options that we can explore feasibly.
Okay, next question from Ruth Bamford. Are MHD models valid at these plasma scales? Surely this is the kinetic scale, therefore you need PIC code.
Andrea, this one is yours.
I have actually, I apologize, but my connection broke for some time. So you were asking if the MHD assumption is valid in these regimes. I mean, I would say yes. And anyway, we will try to let's say model the effects with completely different approaches, like single fluid, multi-fluid, and we will not consider the flow as rarefied, which is something that could be a next step if you want. But yeah, this is the state of the art, and we will not depart too much from the state of the art, because the focus on the project is not really to develop completely new models. It's to try to assess how well the existing ones, maybe with some twists, can help us reproduce the conditions. And actually consider that the focus in this project, at least, is not really on the flight conditions, but on the condition that we will be able to reproduce in the facilities, which are not exactly the same. Like, we are not able to, you know, to reproduce a Mach 20 in a plasmatron. So there will be a lot of things to take care. So let's say in the setting of the experiment, we are able, MHD or a multi-fluid approximation will be good enough for reproducing the experiment.
So Pierpaolo has asked another question, the question now on what is the plasma temperature in this case, and I may add as well the following, which I may not have captured from your presentation: how you any heat generation from I guess from the superconductors and so forth, how is it dissipated then, if there is any heat generation? So plasma temperatures, what are they? And then the heat generation dissipation.
Okay, I don't know about the superconductor, but the temperatures that you typically create in this kind of facilities are around 10,000 Kelvin, which are sort of representatives of the kind of flight conditions that we want to address.
Take the superconductor. Yeah. The superconductors themselves don't generate heat. That's exactly the main selling point, because there is no loss at all from the electricity. There will be a cryogenic system to keep them cool, which will operate at about 50 Kelvin. This is still much higher than the traditional superconductors, which you needed to cool to almost absolute zero. And with the partners that we're working with, Absolute System, we are already building on a heritage of space-qualified cryogenic cooler design. So in terms of that being a challenge for transitioning to a flight model, we'd see that as quite a minimal challenge.
Okay, thank you for that. Superconductors are not actually generating any heat because there is no friction. Okay, another question from anonymous attendees. We have another 3 or 4 questions left. With plasmas, the problem of EM radio waves becomes evanescent near the plasma frequencies and therefore does not propagate. Is that not right? That's the question. And then continues saying, which is what causes the blackout? So what causes the blackout? And then, so how do the ray tracing get around this? Do they factor this in? So you can read the question actually from your screen. There's about 4 different questions in the same question, basically.
Well, when the plasma frequency is higher than the frequency of the signal, basically in a certain direction, because you only consider the antenna is operating in a certain direction, then you get the blackout. How does the ray tracing work? I mean, basically, at least the formulation that has now been implemented by University of Luxembourg using a Snell law. But basically now we are trying to, let's say, to improve a bit the model. I must admit, I'm not the one dealing with the ray tracing, so I cannot really tell you all the details. But in case you really want all the details, there has been a publication recently on Journal of Fluid Mechanics, and in which also University of Luxembourg was involved. And there is quite some explanation about the specific method. So the code is open source and it's called Borat.
If I could just add to that, Andrea, and to answer a little bit more the question, the principle is that we open something called a magnetic window using this shielding, which would be a quasi gap in the plasma through which the signal could propagate, whereas the plasma would usually block it. And with the ray tracing, we can try and predict what path the signal actually takes and how it can be directed through this gap in order to reach the receiving antenna.
So you change the configuration of the, let's say, the shock and in the back of your vehicle in such a way that you basically act on the distribution of electrons, which is actually your input for the ray tracing. And you try to model it in a way that you can let the signal get out, escape, let's say.
Like a maze.
Well, I mean, this is one of the most complicated projects I've been dealing with. So, in that sense, I think that we're going to have a lot of discussions. We still have to, answer all these questions. What else do we have?
Next one for Michael Greslin. How far can you decrease the surface temperature? He says that there might be still high temperatures, so you still need a thermal protection system. So the question is, how much weight do you save in the end, as the space flight is always related to weight?
That's a good question. Andrea, if I say something wrong, you help me. Following. The main principle that we're using to solve the problem is to cause something that we call plasma boundary layer displacement. And this is what is achieved with the use of strong magnetic fields. So by increasing this gap between the plasma layer and the spacecraft, you reduce the heat flux to which the spacecraft is being put under. And this is the key to also reduce the amount of TPS that you need to bring the spacecraft, because without the chill, you will really need more protection, and that's why you will need also more weight to avoid catastrophic failure. So this will be related to the amount of magnetic fields that is going to be allowed in this magnetic shielding. and also to the form of the spacecraft. So it's not a really, it cannot be answered, in a, you will have a reduce of 30%, you see, because it depends of many factors, but you will have a reduce, you will have a decrease, and that is the important thing that you achieve with this type of technology.
Yeah, so you definitely will need, I mean, to put less weight on your thermal protection, but you still need to have a thermal protection. But at this point, it's really, I mean, we are going to test a new technology basically, so we cannot really know exactly how much we will reduce. Let's say if we get a 30% or a 50%, that would be already a big saving in, in thermal protection system, which in some typical configuration can take up to 35% of the global weight of the vehicle. So, you can make the math.
Okay, next one is from Claudio Voto. What is the interference between magnetic field and the cosmic radiation generates their deviation? I think I don't fully understand the question, but that's what the question is saying.
I think there might be a bit of confusion. So at least for this application, it's not interfering with cosmic radiation. It's with the plasma particles, and the deviation is then coming from the fundamental electromagnetic forces, which that's a physical phenomena with the interaction of these charged particles in the plasma and the magnetic field. But it is interesting to mention cosmic radiation because exactly with the same principle, we can potentially solve this issue with superconductors. Cosmic radiation particles are also charged, just like the plasma in the atmosphere when we re-enter. And again, by using an electromagnetic field, we can take advantage of Magnetohydrodynamic phenomena to protect the spacecraft.
And this actually is one of the main obstacles to send men to Mars. So to be able to protect from radiation. So,
but in that case, the question I have is, would you require a quite strong magnetic field to help from solar flares or solar radiation as well as cosmic radiation? Do you require very strong magnetic fields?
I would say so.
I will say so. That will depend, of course, of the spacecraft and the volume that you want to protect. There is a consortium that have done some studies on this topic. It's consortium also led in Italy as
SR2S.
SR2S. You can check it out in Cordis. And the SR2S did already some feasibility studies for using superconducting magnets for cosmic radiation protection. And you will see there are some comparative tables, etc. But this can be seen. If it is wish, please write us. We will send information about this.
Okay, I have 3 more questions if you're happy for me to continue until the end. Okay, so from Pier Paolo, are you saying that there is 0 loss rather than a very small on the superconducting systems? And how do you shield different surfaces or shapes or shape the magnetic field for different kind of surfaces?
Okay, I will take a part of this on this one. It depends of the type of superconducting systems you have. Okay, at this point, the state of the art for example, joints and harnesses is demonstrator levels, and it also depends of the size of the systems. If we're going to be dealing with an airplane that considers a fully superconducting system, then you will have losses for sure, because you will have appliances that are not fully superconducting. Fully superconducting systems are still only at very big scales, especially in power grids, where you can have power, you can have DC bus bars, you can have fault current limiters, transformers, and all of these, if it is fully superconducting, the only efficiency associated losses are going to be coming from the cryogenic systems. But these ones will be overcompensated by the efficiency gain by using superconductors. Okay, so yes, you will have losses, but in systems that are being requiring large amounts of powers, the gains on power density that you will obtain with the superconductors will compensate. Now on how to shield different surfaces or shape the magnetic field, I'm not so sure of what type of shielding. If you know, if we're talking, it depends on what type of cabling or harnessing. I don't know what are we shielding, so I cannot answer. So, but we can take this discussion. I mean, my contacts are there. Pia Paolo, please feel free to send me an email.
Yeah, Paolo is a friend of mine, so if he has a question, it doesn't have your email, I can provide that. I think that the shaping will be resulting of how you distribute your wiring, your sort of cables, your superconducting cable on the surfaces of the spacecraft. That will actually create the composite magnetic field around the shape. I think as an engineer, that's what I would think first, basically, that the shaping will be a result of the superposition of different magnetic fields around the spacecraft where you want to protect during descent. And if, in fact, one of the other questions I personally had, would these very strong magnetic field, although they may not have any how do you say, impact on human bodies, what about electronics on board? I guess the electronics on board would have to be shielded through some kind of a cage in order to avoid the any interference from the outside magnetic field, I suppose.
This is something certainly we're aware of and something which we are working on solutions for. But as you mentioned, and as we mentioned a few times, the ability to really have a much greater control over the shape of the field than is possible with conventional conductors. We are trying to exploit this as a way to avoid the electromagnetic interference. So we get the field exactly where we need it for our purposes and minimize its impact where we don't want it.
That's the freedom of design that the superconductor gives you. You see, you can have superconductors that are as thin as 0.1 millimeters, and they can be 4 millimeters thickness or width, and they can carry up to 500 amps per square millimeter. And that is a tremendous amount of power. Yeah, and that's precisely this advantage is what you can use to modify your design and come up with solutions to existing problems.
Okay, I guess we will have lots of questions on these superconductors. Let's move on to the last couple of questions. Ruth just has a statement saying, in response to Andrea, PIC codes are very well established to simulating kinetic. You don't need to create your own, but MHD and any fluid model will not capture the right physics. Okay, that's a statement from her.
That's an opinion, and for this kind of application, I sort of disagree, because actually, the closer you are to a continuum regime, the more peak become expensive and also unreliable, or at least, I mean, it's like an overkill. I have to stress again that the main focus in terms of numerical capability is to be able to simulate the experiments that we will have. And in that regime, the continuum assumption is absolutely holding. Then if you are considering a re-entry and you are really not too high up in the atmosphere, still we can consider the flow continuum. And I'm well aware that peak is very well established for some application, especially for plasma thrusters in astrophysics. There is even people in my department working on that, but for this kind of application, it would really be an overkill. So I'm pretty confident we we choose the right approach.
Last question. Did you perform any preliminary calculations, or is there any data that estimates the power requirements of the system versus the protection surface area of the spacecraft?
So we have some preliminary ideas about how much power we're going to need to run the system. It will be obviously very case specific, but it will be on the order probably of about 1 kilowatt. This is mainly for the cryogenics. Like I mentioned in one of the previous answers, we're not really expecting that the power requirements will change significantly for different protected areas. You'll need larger superconductors, for example. You might need more current. But at the end of the day, again, because they can take, because they have such high capability for carrying the current, the actual operating power of the system is quite scalable even for larger surface areas.
I think we finished all the questions. Unless you have any last statements, then we can close the session.
Well, we wanted to just show quickly the video that we had. We're working on some animations for the project, as our role is dissemination partners. And we have a beta version, which is sort of 60% complete. And we wanted to just show you guys. We'll be releasing this on our social media soon. So yeah, enjoy this premiere.
MEESST, the Magnetohydrodynamic Enhanced Entry System for Space Transportation. Atmospheric re-entry is one of the most challenging phases for any space mission, and we are working on making it safer and more cost-effective. Space is humanity's next frontier, holding the promise of great scientific progress and immense commercial gain. The first step on that journey is to solidify our presence in Earth's orbit, which is where most spacecraft are currently operating. To stay in orbit, these spacecrafts need to travel through space at hypersonic speeds of at least 8 kilometers per second, which is over 10 times faster than the speeding bullet and over 20 times the speed of sound. Spacecraft arriving from beyond Earth are traveling even faster. Re-entering the atmosphere at these speeds generates enormous amounts of energy in the form of heat. This is because the air molecules around the spacecraft's leading edge are compressed in what's known as a compression shock and split apart, releasing free electrons in the process. This creates a meltingly hot electrically charged gas known as a plasma, which envelopes the spacecraft throughout the early stages of its descent for several minutes, which causes two major problems. First, with temperatures that can exceed 2000 degrees Celsius, the plasma poses a considerable stress on the material of the spacecraft, and therefore to the safety of both crew and payload. Currently, the heat is mitigated through the use of physical thermal protection systems, which are expensive and add considerable weight to the spacecraft, thus reducing the payload capacity and increasing mission cost. They also create a serious risk of catastrophic failure if the protective layer is damaged. Second, radio waves ricochet off the plasma, which leads to a radio frequency blackout. This makes communication between the craft and ground control impossible, leaving the spacecraft cut off from the outside world. The spacecraft can transmit vital data to mission control, who themselves have no means to intervene in case of an emergency, either via radio instructions or remote control. If we want to make space missions both safer and more economically feasible, we need a system that solves these two problems in a way that is cheaper, lighter, and safer. And MEESST promises to do just that.
Okay. Thank you. Thank you very much to the consortium MEESST, to Neutronstar Systems, Andrea, for coming on board today. Thanks also to the attendees who have come to see our webinar. Please look to our website, www.access.space, for any more information if you'd like to join or if you need more information. And if you would like to attend other webinars or be a panelist in the future webinars, please just send me an email. If you need to contact our panelists and you don't have their contact details, just write to myself and then I will provide them to you. Take care, all the best, and have a nice day and week.
Thank you.
Thank you very much.
Thank you very much,
And
everyone.
stay safe. Bye-bye.
Bye.
Bye bye.